Alright, so this set of notes in 6.3 focuses specifically on counting examples where we're dealing with a sequence of letters or numbers. Alright, so the letters in the word computers, alright, so this is the word, and instead of using all 36 letters in the alphabet, we're only using the letters C-O-M-P-U-T-E-R-S, computers, only those 9 letters, to be used no more than once each to form a sequence of 4 letters. Alright, so this is the sequence of 4 letters. Sequence means order is important. If I draw the letter C-O-M-P in that order, that's different than the sequence C-M-P-O. It would be different if I reordered it. It's kind of like a code, right? Sequence means your phone number is a code. You have a certain set of numbers. Somebody else might have the same numbers as you, but it's in a different sequence. It has to be in order for your number to be unique. Same thing's true here. Alright, so sequence means order is important. Right, and then there's this phrase, no more than once each, meaning once I've picked a letter for my sequence, once I've picked the letter C, I can't pick it again. I can't get 2 C's in my sequence. I can only have 1 C. Alright, so no repeating letters. Alright, so order is important, no repeating letters. Now, in 6.4 we will learn an alternative method to this, but I think this is a good one here to use for our and ors. And a lot of times it's easier actually to do it without what we're going to learn in 6.4. Alright, so the first question is, how many different sequences can be formed? So this would be my universal set, right? That would be set S, and we want to know the number in my universal set. Alright, so just to list down what I can't repeat letters, so no repeating. Order matters. And we have 9 different letters. Right? And it is important that they're different. And whenever I do sequence examples like this, I always pick words with letters, with different letters. There'll never be a repeat. There won't be 2 C's or 2 P's in the word. Alright, if you look at it, the word computer has 9 different letters. There's no repeats at all. Alright, how many different sequences can be formed? Well, we want a sequence of 4. We're going to pick 4 letters total. Alright, so that's sort of the important information. No repeats. The sequence of order is important. 9 different letters I can choose from, and I'm going to pick 4 of those 9 letters to get my sequence, right? C-O-M-P is an example of a sequence of 4 letters based on the letters in the word computers. Right, what you can sort of think about it is the 4 letters that I'm going to pick can be thought of as places. There's the first place in my sequence, the second place in my sequence, the third place, and they're picks. I've got my first letter to pick, and my second letter to pick, and my third letter, and my fourth letter. And so when we set this up, a lot of times what I'll do when it's dealing with a sequences of letter numbers, I'll draw a little line with a dot and for how many I have to select. Alright, those are my places in my sequence. This is the first pick, and that's why there's a multiplication. This is the second pick, and this is the third pick, and this is the fourth pick. Alright, so the little dash lines means those are my spots in my sequence. This is the first spot in my sequence, this is the second spot in my sequence, the third spot, and the fourth spot. And that's how I'm picking them, in that order. Right? That's the order I'm going to place them in my sequence. Alright, so in the first spot, I can pick any of the 9 letters, right? I can pick any of the letters from the word computer in the first spot. So there are 9 choices for the first letter in my sequence. And then, since there are no repeats, if I've picked a letter, I can't pick it again. So if I've picked M in my first pick, it can't be picked in my second pick. And so how many letters are left over then for my second pick? How many choices do I have for pick 2? I've got 1 less, right? I've only got 8, and then that works for the next one, right? I've picked 2 letters now. For the third pick, I've got 2 less, which is 7, and then for the last pick, the fourth and last pick in my sequence, Well, I've already picked 3 letters and I can't pick them again. And so that means there's only 6 left over for that 4th place. And so the sequences that are possible from my 9 letters is 9 times 8 times 7. 6 comes from, I have 9 choices for my first and 8 choices for my second and 7 for my third and 6 for my fourth. And so then you multiply those out, 9 times 8 times 7 times 6. And will give me a total of 3,024 different, 3,024 possible 4-letter sequences. Alright, and again, that would be my universal set. That's the total. That's the most, which is quite a lot, right? I have 3,024. It would take me a long time to list 3,024 different sequences. That's how many there is. Right? If I did, that's how many. If I put them in a computer algorithm and had the computer list them for me, that's how many there should be in my list. Right, that's the universal set for this case. Right, so same case, but now I'm going to do subsets of this case. Right, so all of the remaining examples from this one should all be less than 3,024. Alright, I want to know how many of these sequences, the 3,024, contain no vowels in them. Alright, out of my 3,024, what's the odds of not having a vowel? How many of them? Well, I had 9 letters total, right, in the word computer. If you go back and look at the word computer, 3 of them are vowels, right? The O, the U, and the E are vowels, which means 6 of them are not vowels. So in the 9 letters, there are 3 vowels and 6 that are not vowels. They're consonants. Alright, and these are the ones I want to select from. I'm limiting myself to those 6, right? Instead of picking all my letters, I'm only going to pick the 6 that are vowels. Alright, so I want the number of sequences. I'm still going to select 4, but all 4 are going to come from the non-vowels. So I'm going to pick 4 of those. So again, I have my 4. I'm running out of room there. Alright, and there's multiple, those are my multiplications, right? This is the first pick, second pick, third pick, fourth pick, and it's all and. I have to pick the first letter that's not a vowel, and the second letter that's not a vowel, third letter that's not a vowel, and the fourth letter that's not a vowel. Well, this would be the first letter that's not a vowel. There are 6 possible choices that are not vowels for my first pick. And then just like before, well, I've already picked a non-vowel, I pick a consonant. So for the second letter, well, there's 1 less. So there are only 5 non-vowels left over for the second, 4 for the third, and 3 for the last. And so it's 6 times 5 times 4 times 3, and I'm going to write my answer up here. So 6 times 5 times 4 times 3 is 360. Alright, so there are 360 sequences of 4 with no vowels out of 3,024. So again, eventually where we're going with this is, well, what's the chance that happens? Well, I've got 360 chances out of 3,024. Alright, next example. How many sequences contain the letter N? Alright, now it seems like a simple question, but there's actually a lot involved in this one. We're actually going to come at this one in a slightly different way than we did the first 2. Alright, I know I want the letter M, right? So I have to pick the letter M. So number of ways where I'm going to get the letter M. So I'm going to say this is my subset. Alright, subset M. Well, there's a little more involved in this because I have to pick the letter M, but I don't know where in my sequence the letter M could be, right? M could have been picked first, or M could have been picked second, or third, or fourth. And so there's sort of 3 parts to this. There's the pick the letter M, how many places can I put the letter M, and then what's left over do I still have to pick. Alright, so the first thing we do, well, we pick what we want. We pick the letter M. Alright, because that's what we want. I want to make sure I pick a letter M because that's what I'm asked to do. Alright. But they didn't tell me which pick I placed the letter M in. And so the second part of this is place how many places can you put the letter M in the sequence? And then the third part of this is, well, I still need to pick 3 more letters that are not M and not repeated. Alright, so this is sort of how it's broken down. Well, first, there's only one letter M I can choose, so that's 1. How many places can you put the letter M in? Well, M could be in the first spot, or the second spot, or the third spot, or the fourth spot. And so there are 3 places that I can place the letter M in the sequence, right? That's the list of them above there. There are 3 places, 3 choices where M can be placed in, right? It could be in the first spot, first pick, second pick, third pick, or fourth pick. All right, then I still have 3 more letters to choose, right? So this is more like what we did at the beginning. My 3 more letters I have to choose. That cannot be the letter M because I've already picked it. And I still can't repeat my letters, all right? So for the first spot to be filled with a letter that's not M, well, I would have had 8 choices for that, right? Because there are 8 other letters besides M. And then the second spot has 7 choices because I've already picked 1. And the third spot has 6 choices. And so there's the multiplication that I'm looking for. 1 represents, there's 1 letter M I can pick. This 4, and this is the 4 students forget, right? It didn't tell me when I picked letter M. So I had to not only pick letter M, but I had to pick him and place him somewhere in my sequence. And depending on where he was in my sequence, I have a different answer. And so there were 4 places the letter M could go. And then I have to finish out my rest of my letters. Finish out my sequence, filling in the rest of my spots with non-M's. Right? And so it's 1 times 4 times 8 times 7 times 6. So the number of ways to get a sequence with the letter M, if I multiply all those out, comes out to 1,344 sequences with the letter M somewhere in the sequence out of my 3,024. Right? So what's the odd I get a sequence with it? And this would work for, I picked M, but it would actually work for any letter. If I wanted a specific letter to show up in my sequence, the odds of that happening are 1,344 out of my 3,024. Alright, so that's how many groups have the letter M in them. Somewhere in them. First, second, third, or fourth spot. Alright, the next one's very similar to that, except it's just slightly different. Alright, but the slight difference is important. Alright, how many of the sequences contain exactly 1 vowel? Alright, so same kind of setup. Number of ways to get 1 vowel. Well, first I have to pick a vowel, just like I picked the letter M. And then it didn't tell me where the letter vowel showed up. Alright, so then I have to place the vowel in the sequence. Alright, how many ways can I do that? And then I've picked my vowel and I've placed my vowel, and that's the only vowel I want. But I have to finish my sequence. Right? My sequence has 3 letters in it. I picked a vowel, that's 1 letter. And so I still need to pick 3 more letters. That are excuse me. Excuse me. I have to pick 3 more letters that are non-vowels. Alright, 3 more letters that are not vowels. Alright, pick a vowel. place the vowel in my sequence, and then pick 3 more letters that cannot be vowels, and again, remember, no repeats. Alright, well, this one's a little different than the last one because I picked one specific letter. This time, I have more than one option for a vowel. Remember, my vowels were O, U, or E, right? So I had 3 options for vowels. There's 3 choices. I could either pick the letter O for my vowel, the letter U for my vowel, or the letter E for my vowel. And so this time, instead of 1 option, there are 3. There are 3 choices for my letter vowel. The second part, however, is exactly the same. I could place the vowel either in the first spot, or the second spot, or the third spot, or the fourth spot. And so there are 4 places where the letter vowel could show up. Where the vowel could show up. 4 places where the vowel could show up. And then to finish this off, I need 3 more letters that are not vowels, and again, I can't repeat. Well, remember, there are 6 letters that are not vowels, and so for the first letter, there are 6 options. Then there are only 5 for the second non-vowel, and then there are 4 for the third non-vowel. And so exactly 1 vowel in the sequence where I have 3 options for vowels, 4 places to put it in, and then I finish it out with the non-vowels, which there were 6 of those, and no repeats. Multiply it out. So 1 vowel sequence, well, 3 times 4 times 6 times 5 times 4 comes out to 1,440 groups. Out of my 3,024, there's 1,444 sequences that contain exactly 1 vowel somewhere in it. Either it contains U somewhere in it, E somewhere in it, or O somewhere in it. On your own, alright, try to figure out how many sequences can be formed if you cannot pick the letter C, so basically letter C is thrown out, and you pick the letter M, but you place it on an N, and I'm just going to, on an end means there's 2 ends to my sequence. M can either be on the first end or the last one. So those are my ends, right? The first spot is an end and the last spot of end. So that's what I mean by ends. There's 2 places the letter M could show up. And then I also have this. So see if you can't figure that out on your own. Alright, like I said before, if you go and look at the filled in notes that I'll be posting later on after this video is supposed to be watched, you can have the answer to that there. Alright, the next example. So that was an example of sequences of letters. The next example is going to be of sequences of numbers. Alright, it works similar, but there is going to be one major difference between this example and example 1. Alright, Social Security numbers, right? Everybody has a Social Security number, or an ID numbers work the same way, or phone numbers work the same way. Alright, Social Security numbers, ID numbers, and phone numbers are all sequences of digits. Social Security number is a sequence of 9 digits. Whenever we use the term digits, we always, unless told otherwise, right, we always assume the digits are 0 through 9. So there are 10 digits total, right? Digits are always 0 to 9 unless you're told otherwise. And the other thing to make a note about this is nowhere in there does it say I can't repeat a digit. Right, that's what's different than the last example. Sequence still means order matters, right? But you are allowed to repeat digits. And I'm going to have a video based on the difference between repeats and not repeats because it's important. All right, and this is kind of a case where this is sort of the same. The first one I couldn't repeat the letters. This one I can repeat the digits. Right? Somebody could have the same number as you in their Social Security number, but the sequence is different. It's the sequence that makes theirs different. They may have the same numbers, but their numbers would show up in a different sequence. Same thing for your phone number or your ID. You're allowed to repeat numbers. All right. But because it's a sequence and order matters, any different sequence of numbers, right, gives you a different Social Security. All right? But it does change how we solve this. So we want to know the total. How many possible Social Security numbers are there? Right? We have, in the United States, about 300 million people would have a Social Security number. I want to know how many total Social Security numbers could we have if we stick to the 9-digit sequence? All right, so Social Security number of Social Security. All right, well, we have 9 spots to fill. All right, we have the first spot in the Social Security all the way down to the 9th spot. 2, 3, 4, 5, 6, 7, 8, 9. And it's right? I have to fill out, my Social Security number has to have 9 digits. All right, so I have the first spot in my Social Security and the second and the third and the fourth and the fifth all the way down to and the 9th, right? So it's a multiplication. Well, the first spot has 10 possible choices, right? Because I can fill in the first spot with any of my digits, so I have 10 choices for the first spot. Well, since I'm allowed to repeat, right, even if I pick the letter number 2 for my first spot here, I could pick 2 again if I wanted to. I could have a whole Social Security number with the same number, right? 2, 2, 2, 2, 2, 2, all the way down if I wanted to. They do try to avoid those, but you technically could. And so what happens here is I get 10 possibilities for each and every spot in the Social Security sequence, right? I've got 10 options, 10 digits that I can pick for the first spot all the way down to the 9th spot. So it'd be 10 times 10 times 10 times 10 times 10, 9 times. Well, there's a shorthand for that. 10 times itself 9 times can be rewritten as 10 to the 9th power, which sometimes we write it like this. If it was a multiple choice question or fill in the blank question, that would be an acceptable answer. I am going to multiply it out. 10 to the 9th is a number, all right, with 1 and 9 zeros after it. That's what it is. 1. Make sure I got all my zeros. Alright, so there are 1 billion, right, once we reach a population of 1 billion, which we've got quite a ways to go for that, we'd run out of possible Social Security numbers. Alright, so there are 1 billion Social Security numbers possible if we are allowed any digit, and we can repeat any digit. Alright, so that's the universal set. That's the big set. Now, a subset. How many Social Security numbers have 0, 2, 3 or 0, 0, 3 as their first 3 digits? So these are looking at 2 specific cases of digits where they gave out the first 3 digits were 0, 2, 3, and the second case is the first 3 digits for 0. So we have to have those sets, and we're separated by the word or. Alright, so I have the 0, 2, 3, and then I still need 6 other digits. And they can be anything. Or I have 0, 0, 3 in that order, and then 6 other digits. Right? And so I have to pick the set 0, 2, 3, and then I have to finish it out. Right, so I have to have that. And then I have to pick 6 other digits to finish it out. Well, there's only one way to put 0, 2, 3 in that specific sequence. All right, so there's only one way to get 0 in the first spot, 2 in the second spot, 3 in the third spot. And then I finish it off with my 6 remaining digits. And those 6 digits can be anything because I'm allowed repeats. And so those would all be 10s. Alright, I've got 6 spots to fill in with 10 digits. And so this would be 1 times 10 to the 6th, or 10 to the 6th. Or, so now we have an addition. This one works the same way. Right? There's only one way to get the 0, 0, 3 in that order. And then I'd still have to finish out my set with 6 digits. But they can be anything. 10, 10, 10, 10, 10. And so that one comes out exactly the same. It's 1 times 10 to the 6th, which is 10 to the 6th. Alright, so there's 10 to the 6th that have the first 3 digits 0, 2, 3, and there's 10 to the 6th possible Social Security numbers with the digit 0, 0, 3 as the first 3 digits. And the shorthand for this would be 2 times 10 to the 6th Or if I multiply that out, it would be 10 to the 6th plus 10 to the 6th, which is 2 million. All right, there are 2 million possibilities. There's 1 million of the first case plus another million of the second case. There's 1 million of each of those, right? This is 1 million. 10 to the 6th is 1 million. Plus another 10 to the 6th, another million. And so altogether, there are 2 million Social Security numbers out there with those 3 digits, right? If they're all out there and being used, with those 3 digits. 0, 2, 3, there's a million of those, and 0, 0, 3, there's a million of those. Alright, the next example. How many Social Security numbers are possible? Alright, so suppose they decide to make a rule where no 2 adjacent digits can be the same. Alright, how many possible Social Security numbers would there be if they didn't allow 2 adjacent digits to be the same? And so what we mean by that, I'm going to do an example just to help you understand what we mean by no 2 adjacent. Alright, so suppose for the first number I pick the number 4, meaning the next number in the sequence cannot be 4. Alright, but I can pick any other number I want, so suppose I pick 3. Alright, then the third number in the sequence can be any number but 3, right? I can't pick 3, so I could pick 4 again if I wanted to. Right? And then the number after that, well, I can't pick 4, but I can pick 3, and so I could keep going that way and finish filling mine out if I wanted to. And that would be an example, now let's say, again, a very special case, but that's an example of where no 2 adjacent digits are the same, right? Make sure I have 9 numbers up there. And so keep that in mind when I fill this out. Alright, so the number in this event would be, I have my 9 spots, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And they're all going to be multiplications because I have to fill out first spot, second spot, third spot, fourth spot, fifth spot, sixth spot, and so on. For the first pick, I could pick anything, right? For this first selection, I had every number at my disposal, right? So there were 10 choices for my first pick. But that wasn't the case for my second pick, right? I had to pick my second pick, couldn't be whatever my first pick was. And so there were only 9 of those. My third pick, well, I got my first pick back, but I couldn't do my second pick. So I got the 4 back, but I wasn't allowed to use the 3, and so there were 9 of those. And that process basically continues all the way down. Whatever this number was, I can't pick it, but that's the only number I can't pick. So there are 9 options for every number after the first digit. All right, the first digit's the one that has 10, and then there are 9 options for the remaining 8 digits. And so if I write this shorthand, it would be 10 times 9 to the 8th, right? Because there are 9 8s there if you count them. And that would be one way you could write it, or you could multiply it out. If you multiply it out, be very careful. Alright, so there would be a little over 430 billion, right? Which, since we have about over 300 million people, this probably wouldn't be a very good idea. We'd run out of Social Security numbers faster. But if we decided to do that, this is how many we would have. Alright, there would be 430, a little over 430 billion different Social Security numbers. Right, telephone numbers work exactly the same way, except it's 7 digits, right? Telephone numbers, if we don't count the area code, all right? So not including the area code. 7-digit telephone number is a sequence of digits. All right, and I want to know how many possible telephone numbers there are in the world that can exist in the world that have the first 3 digits being any of those 4 sets: 821, 827, 834, 836. You are allowed repeats, and you can use any of the 10 digits. All right, 0 through 9 can all be used. All right, so keep that in mind when you fill that out. And again, I will post an answer key to that later. All right, so that finishes up this video on sequences. So if you're going to practice sequences, this would be a video. If you're having trouble with those, this would be a video you want to make sure to come back and look at. All right, sequences are very common counting and probability examples. You'll see these over and over again. All right, we'll stop that here.